Hi guys, I am Yashodhan Agnihotri, a final year student at IIIT Pune, and I will be your host for today. Welcome to our channel, Learn Competitive Programming with CodeChef. On this channel, we post weekly problem explanations and concept videos. Also, if you are interested in competitive programming and want to master data structures and algorithms, this is the place for you. So, what are you waiting for? Click on that subscribe button and kickstart your journey towards competitive programming today. So we are back with an interesting problem from the March Long Challenge 2021. The problem name is maximum topological sort. The difficulty level of the problem is medium and the prerequisites are trees and dynamic programming. So let us see the agenda for today. First, we will try to understand the problem statement. Next, we will see the sample case explanation. Then we will see how to find the topological orderings. Next, we will see the relation between TU and TC. Lastly, we will see why centroid will have maximum topo orderings, and after that, we will see the C++ implementation. Now, let us try to understand the problem statement. Chef has a tree G with n nodes numbered 1 to n and n minus 1 directed edges. Since it's a tree, it will have n minus 1 edges. For each node u in the tree, he can assign directions to the edges in such a way that u is reachable from all the other nodes. Okay, so let us see a simple tree. Let 1 be the root of this tree, and so we select 1 as our u and let us assign directions. So we give directions in such a way that 1 is reachable from both 2 and 3. So now let Cu be the number of valid topological orderings in the resulting directed acyclic graph. So what is a topological ordering? So a topological ordering is basically an ordering in which no ancestor of the current node appears before the node in that ordering. Okay. So in this, the ordering can be 2, 3, 1 if 1 is the root, or it can be 3, 2, 1. So for u is equal to 1, that is for node 1, we have C1 is equal to 2. That is, we have two topological orderings. So now this way, Chef obtains n pairs C1, 1, C2, 2. That is, he calculates the number of topological orderings for each node, and he sorts all these pairs in descending order. So we sort like the maximum, the node with the maximum topological ordering, it comes first in the list. Now Chef quizzes us on this list. What he wants us to find is the kth pair in the sorted list. Now Chef has made our task easier. Now he's only asking for two values of k, that is the largest pair or the second largest pair. Cool. So now since the number of topological orderings can be very large, we have to compute it modulo 10 to the power 9 plus 7. So now let us understand the problem statement better with the help of a sample case. Let us see the following sample case. So here we have a tree given to us. So this is the tree. Now let us consider that the tree is rooted at 1, and let us find the number of topological orderings, that is T1. So let us write them one by one. So the first one will be 2, 4, 5, 3, 1. This is one valid ordering as it follows the condition that no ancestor of node occurs before in the list. The next one will be 4, 2, 5, 3, 1. This is again a valid ordering. One more possible ordering will be 4, 5, 2, 3, 1. Again, another ordering will be 4, 5, 3, 2, 1. Now, similarly, there will be 4 more orderings, and now in this, the places of 4 and 5 will be swapped. Since 4 and 5 are children of the same node, they can be like swapped among each other, and it will like still maintain our topological ordering condition. So this will be 2, 5, 4, 3, 1. This will be 5, 2, 4, 3, 1. This will be 5, 4, 2, 3, 1. and lastly this will be 5 4 3 2 1. So for node 1, we have C1 is equal to 8. Now similarly you can like find for the other nodes 2 3 4 and 5. So if you calculate, C1 is equal to 8, C2 is equal to 2, C3 is equal to 12, C4 is equal to 3, and C5 is equal to 3. Now you can calculate these values yourself and verify them from here. But now if we are given k is equal to 1 in our input, then the answer will be this. So the answer will be 12 comma 3, because it is the node with the largest number of topological orderings. And if we are given k equal to 2, then the answer will be this. So the answer will be 8 space 1. So I assume that you have understood the sample case, and now with this we will be proceeding to the solution approach. Now let us look at the solution approach. First let us try and calculate the number of topological orderings of a particular node. So now say let node be U. So basically what we are doing is that we are routing this tree at the U node. Okay. So it is obvious that in its topological ordering there will be something like x1, x2, x3, and at the end it will have a node U. So basically what we are doing here is that before we put the node U in its topological ordering, we are putting all nodes in its subtree. So we are putting each and every node in the subtree of U, we are putting it in its topological ordering, right? So basically what we have the subproblem at hand is that we need to place each node in its subtree in the ordering. So let us consider something like this. This is the node U, this is its child C1, C2, and say C. Okay, so we have C children for the node U. So here now let us convert it into a DP problem. So here let DP of C1, let it represent the number of topological orderings at the C1 node. Okay. So like once we get the number of topological ordering at each of its children, then we can find the topological ordering for U. So it can similarly be reduced to the number of topological orderings for the children of the C1 node. So let DP of C1 represent number of topo orderings at C1, and similarly like DP of C2 will be number of topological orderings at C2, and similarly. So now what we can do is we can calculate DP of U. So DP of U will be the number of topological orderings at node U, right? So while calculating DP of U, we need to keep in mind a few conditions. Let us see what those conditions are. So these are the conditions that are required to calculate DP of U. What is DP of U? DP of U is the number of topological orderings for a tree rooted at the U node. Okay, so the first condition is that the relative ordering of nodes should remain same. So this is pretty obvious that the relative ordering in any subtree, like if the relative ordering is say A, B in one of the subtrees, then in the final answer for DP of U, the relative ordering between A and B should remain same. It should not happen that B comes before A, because this will violate our condition. So let us move on to the second condition, that no ancestor of a node should appear before the node. And this is a pretty obvious condition because this is the definition of a topological ordering. So this should be followed. And lastly, the node U should appear at the end of the ordering. And this is also obvious because it is the root of the tree. So it should obviously occur at the end of the topological ordering. Now let us see what the DP expression will turn out to be. So this DP expression is obtained by intuition, and I will also try to give a small proof for it. So let us see what the DP expression is. So we get the following expression from observation and intuition. So let me show what this expression is. That DP of U, where U is a node in the tree, where DP of U is equal to the multiplication of DP of child of I. So child of I is the child of the Uth node into SS of U minus 1 factorial. So SS is the subtree size of U divided by, again, the product of all the factorials of the subtree sizes of its children. Now let us see a short proof from where this DP came from. So for the proof, let us start with an example. Let us take our node U and let us take it as three children, C1, C2 and C3. So what is the number of topological orderings for node U? So TP of U is equal to, it is obvious, it is equal to 3 factorial, because all these nodes can be interchanged as in how we want them to. So dp of u will be equal to 3 factorial. So if we have any node which has which is like the pre-leaf node, so which has its children as the leaf nodes, right? So a pre-leaf node, so let us consider a tree which is rooted at u, and it is something like, so here we have the node x, it is a pre-leaf node, and let us consider the leaf nodes as v1, v2 and so on. So we already know that the dp for the leaf node, it is equal to 1. Therefore let us see what is the dp for x. So dp of x, what is the dp of x? Dp of x is equal to, so let us say it has k children, so dp of x will be equal to k factorial. Now what is k exactly? So dp of x is equal to the number of nodes in the subtree of x, which is again k plus 1 because it includes x node itself. So ss of x minus 1 factorial. This is our dp of x. Now let us consider the node above x. So let this node be, say, y. So dp of y will be equal to, let me just scroll it. So dp of y, let us consider it has children x1, x2, x3 and so on. So dp of y will be equal to, now we take the sum, the product of all these nodes x up to xc, so c, and it will be dp of x of I, and we know what x of I is, we have seen it earlier, right? And it will be the subtree size of y minus 1 factorial, again we saw why this term comes up, divided by the product of its children, so they are subtree size factorials, so again it will be ss of xi factorial. Now what this can be thought of as? This can be thought of as you have solved those permutation problems that we have been given a sequence, like sequence is 7 3 7 2, it's random 2, and we have been told to find the number of permutations of this. So it will be equal to 5 factorial upon the repetitions. What are the repetitions? 7 7, so this is 2 factorial upon again 2 factorial. So this is exactly what we are doing over here. So this is our root, which is we are writing it as 5 factorial, and this is nothing but we are considering repetitions and we are cancelling them out from the total root permutation, right? So we get this through dp and intuition, and I gave a short proof of how this statement came up. Now that we know the value for dp of u, which is basically the number of topological orderings for node u. Now, once we know this, now let us go on and let us find out how we can get the maximum topological ordering and the second maximum topological ordering. So let us see the a short like proof for that. So before going to the maximum and second maximum topological orderings, what we have done till now, that we can now calculate dp of u. So dp of u essentially gives us tu when u is the root, right? And so we can calculate the value of say t1, t2, like in the question it was given c1, c2. We can calculate it for all the nodes. So here there is a problem that this operation it has cost on, or maybe time complexity on, and if we do it for each node, then the time complexity will become O of n square. So this will be enough to pass subtask 1, and as we calculate it for each node, then we can easily take the maximum and second maximum for our answer. So this will be enough for subtask 1, and it is pretty easy to calculate it for each node. By it we can do it by running a simple DFS over all the nodes and calculate the value of TU for each of them. So the time complexity for this on square, and it will be good enough for subtask 1. Now let us see what modifications or optimizations we can do in this for subtask 2. So now for subtask 2, let us start by saying that we know that we can find dp of u for any node. So now if we root the tree at u, then we can find tu, right? So tu is equal to product of I is equal to 1 to c dp of c of I into ss of u minus 1 factorial. We already discussed that ss is just an abbreviation I'm using for subtree size. I is equal to 1 to c, where subtree size of ci factorial is in the denominator. Now over here, what is ss of u? Ss of u is nothing but n, and this is pretty obvious because u is the root. So we can like rewrite it like I is equal to 1 dp of c of I and into n minus 1 factorial divided by I is equal to 1 subtree size of children of u children ci factorial. Now what the next step we have to do is that let us now root the tree at c1. So now we have found out what is the tu by rooting the tree at u. Now let us root the tree at c1. So c1 is one of the children of node u. So when we root the tree at c1, then c1 is parent of u now, and right, this is pretty obvious, right? So now let us see how we can find the number of topological orderings for c1. Now the new subtree size of the uth node, which was the root earlier, as you recall. So now the new subtree size of the uth node, it is n minus the old subtree size of c1. So when c1 was not the root, so this is the new subtree size of the node u. So we can just adopt a new naming convention that ss new of u, it is equal to n minus ss old of c1, right? Now let us try and find the topological orderings for the node u when c1 is the root. So essentially we are finding dp of u over here. So tu is equal to summation of I is equal to 2 to c Now remember, I is equal to 1 is no longer the child of the uth node because now it is its parent. So because we have rooted the tree at C1. So I is equal to 2 dp of child of I. I am just writing this for simplicity as it will get confused between if I write Ci into we replace subtree size of new. So n minus ss old child 1 minus 1 factorial divided by like we saw the product of again these nodes from I is equal to 2 to C, where it is again ss of old Ci. So let us write the child I factorial, right? So we got our tu. Now here we know that C1 is parent of u, right? C1 is the parent of uth node because we have now rerouted the tree at C1. Now t of C1, it will be equal to dp of C1 divided by ss old C1 minus 1 factorial, right, into dp of u into n minus 1 factorial upon n minus ss old ss old C1 factorial, right? Now what we will do over here is that we know what is the value of dp of u. It is tu, right? So we will substitute this expression over here. So this will get pretty lengthy. So to avoid that, I will directly tell you what our answer we will get. Tc divided by tu is equal to ss of c upon n minus ss of c, where ss represents again subtree size. So this is the final relation that we get between tc and tu, and you will soon see how useful this is in the further case. So we have obtained this expression where we get the relation between Tc and Tu, where Tc is the number of topological orderings for a child of the node U, right? Now let us consider that Tc is greater than Tu. So over here we can clearly see we get that Ss of C upon n minus Ss of C, this is greater than 1, which means that Ss of C is greater than n minus Ss of C, which in turn tells us that Ss of C is greater than n by 2, right? Now what does this tell us? That Ss of C is greater than n by 2. So basically we can change our node U to C. So now let us root the tree at C, so that now we can get a better distribution of the subtree sizes of its children. Now let us imagine that we reach a node where Tu is greater than or equal to Tc, right? Here what we get that Ss of C, it is now less than or equal to n by 2. So do you know what this means? It means that the subtree sizes of each of the children of a node, it is less than or equal to n by 2. This means that the node U is the centroid of the tree, and since it is the centroid of a tree, it will have all the subtree sizes of its children less than n by 2. So centroid of a tree is what we want for our maximum value. So Tu will be maximum if U is centroid of tree. So now we can easily calculate the centroid of a tree. Now the problem remains that how to calculate the second maximum element. So let us see how to calculate that. Now that we have found out that if k is equal to 1, then our node will be the center of the tree and it will have the maximum TU as we proved earlier, because it has the like maximum subtree size, right? So now let us see what will be the answer if k is equal to 2. It is pretty obvious that the node should be adjacent to u, that is adjacent to the centroid. And what node is adjacent to the centroid? Obviously a child of centroid. Now which child should it be? So now again this is very obvious that it should be the size with maximum subtree size, right? It should be the child with maximum subtree size. What can be the maximum subtree size over here? It can at most be n by 2, because as we saw the subtree size of like of all children of centroid will be less than or equal to n by 2, right? So maximum subtree size over here will be at most n by 2. So now we have found out the answer for both k is equal to 1 and k is equal to 2. So this concludes our solution approach. Now let us move on to the C++ implementation. Also, before we see the C++ implementation, let us have a quick discussion on the time complexity. So here On is the time required to find any value of like any topological ordering, number of topological ordering for node U. And here what we have to do, we can already pre-calculate what the centroid of the tree will be. So it will be calculated in again O of V, and again so V is the number of vertices, and again it can now then we can directly calculate O of n. So it will be O of V plus O of n. It is actually O of n, like the overall complexity it will be O of n, including the DFS and all. So in O of n we can finish this solution. Now let us see the C++ implementation. Let us now discuss the C++ implementation. So in this, let us start. So here we have a function called subtree sizes. It calculates the size of each node's subtree in this. So given a root, so given the node and its parent, it calculates the size of its subtree. Now get max. So this function, it returns us the centroid node. Okay, so get max returns us the centroid node. So the algorithm for finding the centroid, it is available on the net. So you can check that out. Get second max, what we are doing here is that int u. So int u is our centroid. What we are just doing, that we are finding the node with which is a child of the centroid with the maximum subtree size, as we checked out in the solution approach. Lastly, here we are having a function called get topo count. So here our get topo count function simply gives us the number of topological orderings as we saw through DP, and this is the DP expression, and it is implemented over here. Note that you will have to use modular expressions functions over here, and otherwise you may get like overflow, integer overflow, right? So done with this. Now let us come over to the main. So here again we have pre-calculated all the factorials modulo 10 to the power 9 plus 7. Now here basically we have taken input n and k. N is the number of nodes and k is like the type of answer that we want. Here we have taken input the edges, and we have pushed them into an adjacency list. Now here we have simply calculated the subtree sizes. Next we have found the centroid, which is called the max node. Then we have found the max count, which is the count of the topological orderings of the centroid. Second max node is as we discussed the maximum subtree size child of the centroid, and second max count is its topological orderings. And then we are just checking if k is equal to 1, then we are outputting max node space max count. else if k is equal to 2, then we are outputting second max node space second max count. Now this was the C++ implementation.